Now this is a cute little machine that somebody constructed. All right, and this is supposed to illustrate what we were talking about, free fall. Now, you have this thing suspended by a rope. There's a little cannon over here. It shoots a cannonball. Ordinarily, of course, the cannonball will go up and in some kind of trajectory, parabolic trajectory, right? So it won't go like this. It'll go like along this dotted line over here. Okay, so it won't go through this hole. It'll bounce off the wall and down. That's what he's drawn. Now, this one also, if it shoots, it's not going to go straight like that. Of course, it's going to drop in some way. Okay? But what happens if I cut this rope? I cut this rope. These two cannons are attached to this mechanism, and they're all falling with the same acceleration. What's going to happen? Pardon me? Why?
They're accelerating the same way, so they're not.
Okay? You have to develop a little bit of intuition for that. This whole contraption is moving with the same acceleration down as the cannonball that left this cannon. As soon as it leaves the cannon, it doesn't have any forces acting on it other than gravity. So it has the acceleration of gravity, as does this whole contraption. So basically, they're both accelerating downwards. Now, of course, this one also has a velocity in the horizontal direction. So it's going to move in that way as well, right? But they both have the same acceleration downwards. Now, this one also is given an initial velocity downwards as well. So it has some velocity this way and some velocity that way coming from the cannon, right? But the acceleration downwards is the same as for the contraption itself. So basically, you could imagine that this is standing far away from any kind of planet or any kind of star or any other kind of massive body. There's no gravity acting on it. What would happen over there? If this fires, it will go straight. If this fires, it will go straight, right? If there's no gravity. In free fall, because both the cannonball and this contraption are moving with exactly the same acceleration downwards, there's no reason for one to kind of move faster than the other or one to miss the holes over here. Can you see that? All right? So what happens then is that in free fall, particles move along like geodesics of the 3 space. Okay? And if you draw the space-time, they'll also be geodesic of the space-time. All right? These are straight lines. In other words, in free fall, particles move as though there's no forces acting on them. It's as though there's no gravity. So you have a little bit of this intuition that free particles move along straight lines when there's no gravity. Even when there's gravity, still they move along straight lines if you're in free fall. When do things get complicated? If you're fighting gravity, then you'll suddenly find that things have all kinds of strange trajectories. If you don't fight gravity, you don't notice gravity, and everything is simple. Things continue still moving along straight lines. So the way that this is formulated is physics is simple in free falling frames, or inertial frames in this sense. Okay? It's all simple. There's no gravity. In the same way that you would calculate a straight line trajectory or a straight world line in the absence of gravity. Okay, another diagram showing the same thing. All right, you have a little house on a cliff, and somebody's throwing something through this hole. All right, it's going to go in this kind of trajectory. If this little house is falling at the same time, then of course it will just go straight. Even when there is supposedly gravity, if you're in free fall, there's no gravity, and everything is simple, everything is straight. Of course, the space-time will be curved, and therefore the geodesics are not simply straight lines in the flat sense space. They're a little bit more complicated. They're straightest or the shortest or longest in that curved space-time.